My name is Dominiak from the University of Lucerne in Switzerland. And first of all, I'd like to start by apologizing a little bit. Somehow, with the nice weather in Portugal, I caught a cold and my voice is suffering a little bit, but I'll try my best to get through it. And the technology that I'll be presenting today, I promise, is more robust than I am. So what I'll be talking about is power line communications and data buses. So power line communications is basically sending data on a power network. But first, a little bit general about data buses for safety critical applications. So basically, we're talking here about distributed embedded systems, which typically operate as a closed loop system and have three basic functionalities. Information is gathered from sensors. Information is then processed at a controller, which generates a response and sends that to actuators. So more or less, we could kind of generalize our avionics system into this type of category. But the distributed nature of these systems means that the data bus is really a critical part of that system. And I've broken that down into three different main requirements that a data bus needs to support for a safety critical system. The first is availability. So when the system needs to transmit data, that bus needs to be available, which more or less means that, or goes back to kind of a message loss rate. So the messages need to be transmitted with little loss. Then we have data integrity. So it's very important with any data bus, even the most robust data bus such as Ethernet, we will have errors. It's important though that this data bus detects those errors and does not pass them to the application, because with an application, if it receives data that contains an error, who knows what it's going to do with that? It could be that it performs the incorrect action. So this is really the most critical requirement, something that we have to do with a very, very, very low probability, not pass data that contains errors up to the application. So we need to detect those errors. The third requirement is latency. So we need to deliver the data within a fixed time bound. And all three of these requirements need to be done rather deterministically. That means that the behavior of our data bus needs to be predictable, so we're able to predict what different requirements and with what rate we could fulfill those requirements. So that's just a general introduction, and now I'll focus more on the use of power line communications as a safety critical data bus. So what is the general concept of PLC? Well, basically with PLC, we, in a traditional avionics architecture, which you see in the upper right corner, we have a separate network for data and a separate network for power. What we're doing with power line communications is removing the data network completely. So now we have a single connector for power and data. And the data transmission is independent of the underlying power signal. So there's different power networks in an aircraft. There's 115 volt variable frequency. There's 28 volt DC. Now they're looking at some higher voltage DC also in the aircraft. Our transmission is really independent of that. So our solution would work on all of these different type of power networks. What are the main advantages of PLC? Well, first and foremost, we want to reduce the wiring, weight, volume, and complexity, which will also lead then to a reduced installation and maintenance effort. And one further advantage we could provide, which I'll show a little bit later, the data rates. Compared to the traditional avionics data buses, we could provide a little bit higher data rate. What is the main challenge, though? We need to provide robust and deterministic data transmission over what we'll see as an unreliable medium. So that means that the power line network has not been designed for high-speed data communications. So here we see some of the different problems that could arise in the power line network. Basically, the wiring topology and the impedances at the loads lead to a frequency selective channel attenuation. So these are kind of the graphs you see in the upper right corner. That means that at certain frequencies we have a high attenuation, at other frequencies it's lower, which is challenging for a communication system. We also have a potentially large variation in the received signal strength from different nodes. So if we have two nodes that are connected close to each other on the power distribution network, there's almost no attenuation between them. Whereas if we have nodes that are further apart from each other, then there's a high attenuation. So that means at our receiver, we could have a very strong signal or a very weak signal, and we need to be able to decode both of those signals. It's also the problem that the loads or application devices attached to this network generate additional constant and also transient noise. The cables are not shielded. We don't want to make them shielded because then we lose a benefit from weight. And that has the problem that basically all of these different interferences that could come from our environment will be injected onto our power line, which you don't have with, let's say, an Ethernet network where you work with shielded cables. And then there's further regulations. It's a very strict regulation in the aircraft about EMC, or electromagnetic compatibility. And this basically limits our transmission power, because we need to adhere to these standards just as any other device within the aircraft. Excuse me. Okay, so we have developed a PLC protocol specifically dedicated for safety critical systems, and we've given this protocol a name called Power Line Data Bus, or with the acronym PLUS. And this protocol has been designed, we haven't really worked completely from the bottom up, not reinventing the wheel. We've designed this around proven standards from other industries for the physical layer. For example, IEEE 1901 is an international standard. Around proven standards used in the avionics industry for the bus arbitration. So that's the ARINC 629 standard, which is used on the Boeing 777. In addition to this, we've done our own custom optimizations and integrated additional application protocol layers. And one important thing that we do is we use the available bandwidth to optimize the data availability and integrity. So maybe some of you know power line communications from these wall plug modems that you could plug into the sockets and you have an Ethernet connection coming out. They're really trying to only optimize the bandwidth. So now they're up to gigabits per second and going even higher. We are using that bandwidth to introduce additional redundancy in order to make our solution more robust. So we are not targeting high bandwidths here. And for the Ashley project, which we're talking about today, we have developed a set of prototypes which will be used for demonstration of our protocol on the ventilation control system provided by the partner NOAD Micro. So NOAD Micro will make sure that we have a rather challenging environment to test our protocol in. And we will also be performing EMC measurements together with Airbus Group Innovations in Toulouse, because EMC, which isn't really the main topic of this presentation, is also an important topic that we need to make sure that we have a suitable solution for use in the aircraft. What does a PLC architecture look like? Basically, the idea is ultimately that we introduce the PLC components into the application devices. So here we see kind of a PLC-enabled application device, and we would have our application host processor, power supply unit, which are standard parts of existing application devices. But now we're introducing two new components, the PLC modem and a coupling module. The PLC modem basically consists of two items, a protocol chip on which the protocol is realized, and an analog front end, which performs analog to digital conversion, as well as signal conversion in the analog domain. And then we also have this additional coupling module. The coupling module is similar to an antenna for wireless communications. So it's responsible for coupling the high-frequency PLC signal onto the power line and for filtering the low-frequency power signal so that it doesn't get introduced to our modem, And we also have some transient protection circuits which protect us from the different transients like lightning and the high-intensity radiated fields. Okay, so now I will talk about some of the different physical layer features which help provide us a high data availability. So basically these features are realized in the physical layer with digital signal processing techniques. And here I've shown 3 of them. One is orthogonal frequency division multiplexing. So that is our modulation type. And what that means is that we're basically sending, rather than having a single carrier which we send our data on, we have a number of carriers in our frequency range, and the data is modulated individually to these different carriers. So all in all, if we use the whole spectrum from 2 to 50 megahertz, we have about 1,900 different data carriers. Each of these carriers can be individually configured. So we can adjust the modulation on those carriers, which means how many bits we send on each carrier. We can adjust the transmission power on those carriers. We can also adjust whether or not we use those carriers. So we could turn off certain carriers, and that means that we don't send any signal in that spectrum. Then we also have very powerful forward error correction, which basically means that at the transmitter we add redundant bits, which help us to correct errors at the receiver. So here we see a table showing the different data rates that we could achieve. And these are, remember, physical data rates, similar to what you see with Wi-Fi when you talk about 54 megabits per second. And it's dependent upon which modulation we're using on the carriers. So that's the horizontal axis, and which coding rate. So how much redundancy we have, that's the vertical axis. So we can see anywhere between 20 megabits per second and 144 megabits per second. To be realistic, these data rates are shared between all nodes on the network. So we would need to divide all of these data rates by the number of nodes on the network. They're sharing it. But that's similar to CAN and other data buses. And we will have some additional overhead for MAC. So if you take about 20 to 30% of these data rates, and then you divide by the number of nodes in the network, those are the data rates that are achievable. But you could see, and also the robustness. To the upper left, we have more robust transmission. To the lower right, less robust. So you could see it's fairly flexible. If we wanted to support a less robust system, it is possible to achieve fairly high data rates. Some further digital signal processing is done, which we call receive estimation. So basically, the transmitter will send a known signal, known meaning it's known by all nodes in the network. And at the receiver, this signal will be processed, so it's a preamble at the beginning of the frame. And this is used to do frame synchronization. So the nodes in the network have an asynchronous clock. In order to properly decode the information, they need to synchronize themselves to each other. And the synchronization is done at the receiver using this preamble. Then there's also a channel and noise estimation being done. So basically that's estimating how the channel is attenuated due to this frequency selectivity, also the different delays on the channel. So those are 2 techniques used in order to provide a robust modulation. Then we also have automatic gain control, which is basically that we're detecting what the signal power coming in is and adjusting our gain accordingly. Because as I mentioned before, we could have weak signals, but also strong signals. So a further topic is now data integrity, which is important now that we have strong error correction algorithms. So we need to be able to detect any bit errors that may occur and throw out those packets or mark them as being packets with errors. And here I write, our protocol has been designed to be able to detect errors even when decoding purely random data. So we know that PLC is a difficult environment which could lead to having errors within the packets. A lot of different data buses are designed around the fact that they assume only 1 or 2 bits will be in the air. We assume that, in principle, all bits could be in the air. And even in that extreme case, we could still detect that there are errors. So we have a really robust error detection. And as you see here, we do the error detection at multiple levels. So CRCs, cyclic redundancy checks, are the standard used to do error detection. And we have, excuse me, up to 4 different CRCs that we use. And if any of those CRCs fail, then we mark that packet as being with error. Then now about providing deterministic latency. So that's really a topic for bus arbitration, or deciding who gets to transmit when on the network. So we have taken a peer-to-peer architecture in order to not kind of a master-slave type of architecture. And our arbitration is based on an algorithm from the ARINC 629 standard, where basically the next transmission slot is determined through synchronization to the previous transmission. And this is done based on a series of 3 timers. So each node has these 3 timers running independently, and based on when their corresponding timer elapses, then they know when they're able to transmit in the network. But one very important part of this is that the nodes need to know when the other nodes are transmitting. How do they do that? They use a technique called physical carrier sensing. That's a technique which is also used in the Wi-Fi networks, where they're able to detect when the other nodes are transmitting based on measuring the noise and also the signal on the network. So it's very important that we have a robust physical carrier sensing algorithm, because we do have a lot of noise on the network, and we want to be able to detect the difference between what is high noise and what is a signal. So the algorithm must be able to do that with low latency, so we can't spend a lot of time detecting when it's coming. We want to also maximize the positive detection rate, so we don't want to miss when some other node is transmitting. And we want to minimize the false positive detection rate. So it is possible that we could detect noise as being a signal from a transmitter on the network. And that's part of the reason why we've also introduced very strong error correction. So even should that happen, even if we would detect that noise was on the network, we would start to decode that signal. We've still designed our protocol such that we could detect that that is noise and not some kind of false data that was being transmitted. So what are the challenges with PCS? Well, first of all, detecting the received transmissions with varying signal strength. So we could have a signal which is a few millivolts, or we could have a signal which is several volts. Detecting the received transmissions with a low SNR. So we need to be able to differentiate between noise and signal. And also detecting the PLC transmissions with strong interference. So here I've shown 2 plots. Here we see what a narrowband interferer could look like. And here we see what our signal with that narrowband interferer looks like. What could a narrowband interferer be? It could be a broadcast radio station, which is still received within the aircraft. With our OFDM protocol, in the digital domain, this really isn't a problem. So it only means that we have strong noise on a few of those carriers, and with the redundancy, we could still receive the data. But you see, in the analog domain, there's very little difference between this signal and this signal. We're only talking about a few volts. So this is really a challenge to be able to detect. This is an interferer, meaning no one else is transmitting, and this is our signal. So we need to be able to detect these 2 differences. And I should mention, these interferers, they remain over a long time. So we can't assume that they really come and go. So this is for us a challenge. But we have a rather innovative frequency-based filtering scheme, which we used in order to get around this problem. So some further features that we have. We don't have any protocol management traffic. So we have stateless connections, no network setup time. We've optimized the transport for small messages, so messages which are less than 20 bytes. We support multiple data services which can be multiplexed onto a single PLC bus. So currently we support CAN bus as well as Ethernet. Within the Ashley project, we'll be using the CAN bus. We also have additional optional features which can improve the availability and integrity. We have a physical block redundancy mode where we introduce redundancy on top of forward error correction by sending duplicate physical blocks. And we also provide a retransmission scheme which also works for broadcast transmissions. But both of these are optional and not an integral part of the protocol. So, in summary, a PLC-based or power line communications-based aircraft data bus potentially provides a number of advantages. The Plus protocol has been developed specifically for safety-critical applications by the University of Lucerne. There are physical layer signal processing, which provides robust communications. We provide a powerful error detection. And the bus arbitration provides deterministic behavior. And we have realized this protocol on a number of different prototypes. So, sorry about my voice again. Kind of has gone away now, but thank you very much.